It is a pleasure to welcome you to second edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on AI and Big Data in Geotechnics, which will be delivered by Dr. Robert C. Bacchus, Professor Sarat Kumar Das and Dr. Nick Machairas. Nick is a geoprofessional, lecturer and entrepreneur who ventured into software engineering, modern data management and predictive analytics, operating at the forefront of the digital transformation of the geoprofession. He is the founder of Groundwork A.I, Groundwork A.I, a high-tech engineering venture dedicated to empowering geoprofessionals by offering custom data management and machine learning solutions that can facilitate smarter, safer and more cost-effective infrastructure monitoring, design and construction. Nick's initial research and project efforts focused on applying advanced data analytics to deep foundations and have now evolved to include intelligent assistance that enable synergistic human-machine engineering design workflows. He is currently a lecturer at NYU and Columbia University teaching undergraduate and graduate courses in computer programming, machine learning, modern database management systems, and engineering ethics. Nick is an active member on the ASCE, GI, DIGGS, Deep Foundations and INNC committees as well as the Transportation Research Board Standing Committees on Geotechnical Instrumentation and Modeling, AKG60, and Foundations of Bridges and Other Structures, AKG70.
Yeah, so hello everybody. I have a near impossible task of following suit from Bob and Professor Das. They did an excellent job presenting some really amazing aspects, some really good concepts here. So I'll try to do my best. But I should say my presentation, the way it's structured, and I'll tell you a little bit more about it later on, I developed it based on the theme of these lecture series. And here we see that this is a very successful series on advancements in geotechnical engineering. And I'm focusing on the part where it says from research to practice. So what you'll see is very much my experience of moving from an academician to a practitioner and what this required in order to operate within AI, data, and geotechnics. Before I get started, I have to mention all of our thoughts and prayers are with everyone in India. It's a very difficult situation right now, and it's a horrible virus, and I just hope that this ends very quickly and in the best outcome for everybody. And also very, very quick, the speakers that preceded have the benefit of being very well known, but in my case, I'm lesser known. So I thought I'd do a very quick 1-minute introduction of what I do and what my company does. So my company is on a mission to empower geoprofessionals essentially through data management and machine learning, because there's multiple benefits that can come out of this. And there are 3 main focus areas: limited technical consulting, working with very few clients, high value clients, but most of my time is devoted on analytical models and software engineering, which can then be packaged and as products and services, cloud native services actually, that geoprofessionals can use online. And the third part is training. So that's a big focus. I've been teaching for a while. So I'm using the lessons I learned from teaching to help other geoprofessionals get started with AI and machine learning. Now, about this presentation, it's always a bit of a challenge not knowing exactly the audience, as they say, or how technical or how high level a presentation should be. So in my case, I chose to go the safe way, and my goal here is to inspire you. And again, this is coming from my experiences where I have been in other presentations and in other cases where some really amazing studies were presented. And in many cases, there I felt, where do I get started? And then when I was the person doing those presentations, I had a lot of people come to me and say, I really like what you do. I really like the models you've built. How do I get started? So hopefully with this presentation, if we have some audience members here who do not know how to get started, then hopefully by the end of this presentation, you'll have a very good idea on how you can get started as well. So my passion is absolutely to make AI and machine learning commonplace in the geoprofession. And the best way to convey this passion is to make the case for the digital transformation of the geoprofession. And I'll attempt to do that. I'll also present a few opportunities. There's countless and many challenges as well. And Bob did a fantastic job to presenting data management. But as a person who is actually building custom data management solutions, I also wanted to offer a few thoughts on that as well. All right, so let's get started with the digital transformation. What is this idea? What is this? What is the future of the geoprofession? You hear a lot of people have their own version of the future. So I'm going to focus solely on the vision that includes digital transformation. Also, I should mention the way that this presentation is structured. I start from high level. I start by presenting the challenges to leadership, and then I'll move on to what is required by the people who actually implement this change. So the number one thing that we teach, the number one concept that we teach at Columbia University is that any analytics venture within an organization must be a top-down decision. It must start from the high levels in the leadership, because it's a big commitment, it's a big investment. So they need to be on board fully in order for this venture to be successful. And sometimes some senior executives might not know exactly how to implement the vision, how to essentially enhance the day-to-day operations by including advanced analytics, machine learning, and data management. And that's okay. One of the main characteristics of leaders actually is to know their limits and to know when it's time to seek help. So at that point, it's crucial to actually find and recruit those agents of change, either internally from within the organization, or perhaps outsource the venture to some outside consultants. It's very important, though, not to ignore ambitious employees who can become change agents. I've seen that sometimes where with the younger generation who is much more versed into programming and understands machine learning, it's important to trust those employees and give them a little bit more of an opportunity to present their vision, present the dreams, and essentially implement what could be a very successful analytics implementation. Now, another very important decision is data management. Bob did a very good job presenting that. And I've made this bold and italic. An organization must invest heavily in data management. It's absolutely important. And the reason why, again, leadership needs to be on board is because sometimes we go through the process. You saw some excellent studies that Professor Das did, going from these studies to actually models that can be implemented in the industry, and a company can actually convince their clients that they're reliable enough to use. This is something that takes time and a lot of effort, going from a proof of concept to a marketable a reliable predictive service is a huge undertaking. It's going to take a while, so you should not expect instant results. But at the same time, while you're keeping your expectations in check, it's important to also set really bold goals for the future. Because in the process of achieving those goals, maybe you might not go that far, but still in the process, there's a lot you're going to learn. So this is a quote I like very much, and this is one that I always present when I talk to friends or clients who primarily work with a billable hour model. So I'll let you read here who it's from, but the question is, what is the purpose of a business? And according to this quote here, the purpose of a business is one, and it is to create and keep a customer. And how does a business do this? By focusing on only two functions, marketing and innovation. And the reason why this is important to have both of these functions, marketing and innovation, is because if you have marketing without innovation, it's the equivalent of selling snake oil. But if you have innovation without marketing, it's the equivalent of selling to crickets. So in this case, this fits. I always bring it up, especially again for companies that focus on billable hours, because I like to poke them. And most of the times what I see is there's this concept of good enough, get the job done. And no, I want to make the case here of going a step further and focusing on relentless innovation, because this can pay dividends into the future. So how do we do all this? Does this mean we have to change our ways? Do we have to reinvent new business models and incorporate AI and machine learning? How exactly is this going to happen? Well, I'll tell you right now, we absolutely do not have to reinvent the wheel, because others have done it before us. So we just have to follow their example. And one of those examples that really, really stuck with me is this new type of companies, the new ventures, which are the so-called deep tech ventures. And due to a confluence of innovations and solving big problems and massive breakthroughs, there's a renewed interest in deep tech. The Boston Consulting Group calls it the dawn, actually, of the deep tech ecosystem. And I have some very important links down there. I highly recommend that you read and you watch the video and you read this article when you're going to receive the slide deck. So what is deep tech? Let's start by that. It's mostly a classification of an organization, sometimes a startup company, but this organization has a very specific objective: providing technology solutions based on substantial scientific or engineering challenges. And this is something that usually requires lengthy research and development. So when we're talking about the future of the geoprofession, one that could be tightly related to technology, at the same time, it's easy to imagine substantial scientific or engineering challenges within the geoprofession that could be solved or improved using technology. And one characteristic of deep tech ventures is that they can generate enormous economic value. So if you're here as a decision maker within our organization, I sometimes tend to be very romantic or passionate about the future of the geoprofession, but you can also think of this investment in analytics and machine learning as one that can actually also create immense value at the end. And I quote a lot Antoine Gurevich, and you can look up his TED Talk as an expert on deep tech. And what deep tech is, it's a new chapter in the innovation story, bringing together science, engineering, and design thinking. What are some examples of deep tech ventures? Well, Pfizer, BioNTech providing a vaccine for COVID in under a year is a very good example of a deep tech venture, which combined engineering, science, and design thinking. Now, as I mentioned, this is something that's very attractive to investors. And according to studies, infrastructure and the environment are actually among the most sought after impact goals of deep tech companies. So why am I bringing this up? Just to make the case that investing in machine learning and AI within the Geoprofession is not something abstract. It's actually something that can present immediate results, very quick results. So I twisted this concept a little bit, and I said that instead of presenting it in terms of deep tech, engineering, science, and design thinking, what if we think, we rephrase this a little bit, let's call it deep geotech, perhaps. And what this includes essentially is it's the confluence, a combination of expertise in geotechnics, geotechnical engineering, geoenvironmental engineering, with data science and software engineering in order to enhance existing workflows or create new disruptive services. I have some examples up there of what the intersection of each one of those, each two or more, I should say, of those fields can lead to. So in other words, what this can achieve is to lead actually the digital transformation of the geoprofession through relentless innovation by merging those three fields. And the goal here from a business perspective is to create practical, marketable value from what will be essentially human-machine synergies that provide, that can provide exceptional experiences to your customers. Now, whenever we talk about AI and machine learning within the geoprofession, sometimes I'm actually hesitant to just focus on AI and machine learning, and instead I prefer the term advanced data analytics, because the way I define this term, I include both artificial intelligence and machine learning, as well as automation, optimization through computer programming and statistical analysis. And it's very easy to make a case, and I'll show you a few examples in a bit, of how you don't even need to touch any AI or machine learning and still produce some remarkable results for your company by just enhancing the tools that you use day to day. So remember this, in advanced data analytics, this includes AI, machine learning, and or automation optimization through computer programming. So some very powerful concepts there. Now, Professor Das did a fantastic job presenting some examples, some sort of, not even examples, sorry, some results from remarkable studies with high accuracies and some very practical conclusions. But this is just a slide here for those of you that maybe this is the first time that you encounter AI, machine learning, you just hear the buzzwords, you don't know what this is all about. So let me help you a little bit with this. So artificial intelligence is the study and design of intelligent agents. And an intelligent agent is essentially a system or an algorithm in its most basic form that has some way of perceiving the environment and takes actions in order to maximize its chances of success. This is what AI encompasses. So what it does essentially is it replaces what could be an extremely laborious and time-consuming task of creating handcrafted rules perhaps in the form of an algorithm or a computer program that implements these rules and achieves some kind of an action. So, um, and then an example of this is, let's say, autonomous vehicles. So it is possible to define a million rules by hand that would cover many scenarios that an autonomous vehicle might encounter while they're out there navigating the streets. But a million will never be enough because there are so many other conditions that we cannot envision and we cannot write rules for. And what AI does in this case, by training, by having an intelligent agent that can take actions, it's this agent then that can adapt essentially to unknown conditions and take actions. So at first, we may consider machine learning as a subfield of AI, but that's not exactly it. Machine learning is concerned with the development of algorithms where computers can automatically produce models from data. So let me give you an example of this. Imagine you want to develop a program that can recognize handwritten digits from images. So someone could be asked to look at all of those images, all of those digits, and come up with some kind of a very lengthy if then that rule that will essentially define what number 0 looks like, what number 1, number 3 look like, and so forth. But this is not going to cover how every person might write that digit. So we use machine learning with a big enough data set, and machine learning is actually going to determine how to reach, how to essentially find a way to accurately classify one digit from another. And also very quickly, deep learning is a subfield of machine learning. And as a subfield of machine learning, it refers to a particular subset of models that are very good at certain tasks. So in short, machine learning, deep learning, they definitely help to develop AI. However, AI doesn't necessarily have to be developed using machine learning. And I already mentioned what machine learning is. It's an art, essentially, of building intelligent machines that can transform data into knowledge, or building computer programs that learn from experience. But the reason why here I want to reinforce my belief that we better use the term advanced data analytics rather than machine learning for everything is this essence of machine learning that I came across from Professor Abu Mustafa at Caltech. He has an excellent open sourced lecture if you want to take. So there are 3 conditions that need to be met in order to apply machine learning. There needs to be a pattern. We cannot use any kind of an algorithm to predict randomness. And there are different ways where we can check whether a pattern exists. It needs to be a problem that we cannot pin down mathematically. And this is a little bit in a gray area because you can still apply machine learning for convenience in problems that can be pinned down mathematically, but that's a whole different discussion. But let's stick to this fact. Imagine that the problem that we're dealing with is one where we cannot define any kind of, let's say, polynomial function, no matter what degree this function has, that how complex it might be, that describes problem. Number 3, very, very important, we must have data. There are some recent evolutions in machine learning, and keep in mind, it's a rapidly evolving field spearheaded in many ways by Google in terms of pushing this innovation to everyone. So this innovation has to do with transfer learning. So one of the next steps now where we can perhaps erase number 3 in some cases is reusing pre-trained models and then just adjusting the last layer in terms of what we want to get out of those predictions. But this is something that right now has a very narrow scope. For example, if we have a large neural network trained on human voice recognition, maybe then we can use this model to also classify other sounds that are not related to human speech or recognition, but that's a whole different discussion. So in terms of applications in the geoprofession, the opportunities are endless. And we have a large crowd tonight or today for you. And we can sit here and launch a survey, and I'm sure we're going to get 100 more ideas in terms of the opportunities. So what you see here is a very, very loaded slide, actually, with some of the problems that I find very interesting. My research started from deep foundations, bridging the gap between calculated and measured capacities using machine learning. And I am convinced right now that given enough data, we can absolutely improve the design methods that we're using right now. And this is one proof of concept. I've presented this before, so I'm just providing the high-level summary here. We run a proof of concept for plant capacity prediction using very few load tests, just 213 load tests from a federal data set. And what happened here is essentially what we have is calculated capacities using the most well-known, most used method in the United States as they compare to loads measured on the field from load testing. So on the left-hand side, you see quite a large spread, and this is the reality that we have to deal with nowadays. Essentially massive disparities between calculated and measured capacities. But with machine learning, and in this case, this was such a basic model. What you see there as scores, they're not good scores. This is R squared of 0.7 on the trained set, 0.6 on the test set. That's not a good score, but it's so much better than the approach that's currently being used. And another thing to note here is that for this proof of concept, I purposely oversimplified the model just to make a case. And by oversimplification, what I mean is that one of the features, this was trained on just 7 features, and one of those features was just an average SPT blow count along the side of the pile. So that's massive generalization for the site conditions, but still performed pretty good. Now, another example here is deep learning for soil classification, and it's an area that I find has tremendous potential. So when I was at NYU, we had some very fancy, very expensive equipment in the lab. And one of them, what it did is it was essentially a high-speed camera with a microscope. We would feed sand at the top, and then there was a series of tubes, and it was using the Bernoulli effect to essentially separate every speck of sand and push it with air, compressed air through in front of the high-speed camera. And what the camera did, it would essentially take pictures of every single particle in that sample that we fed. So I had an idea there. I said, what if we use those images for soil classification? So we had 5 types of sand, ranging from rounded all the way to angular, and different sizes as well. And I'll tell you how we overcame that problem. And the idea was, can a model classify a sand particle just by a 2D projection, just by a single image, single speck of sand? And the way we did this is we built this pretty large deep learning model. This was using convolutional neural nets. The innovation in this model that I'd like to point out is, there are many ways to classify sand by taking metrics such as angularity and whatnot, convexity and so forth. But the idea is, if all of this information can be derived by the model from just the image. One thing that's lost, though, from 2D projections is scale. How large is one particle relative to the other? So in order to overcome this, what we did is, before we went to the last layer, the softmax layer that would produce a classification, there was a dense layer there where we added the diameter as metadata into this model. And this did, in fact, increase the accuracy. It wasn't perfect. Still, it was around 85% accuracy. But I find this remarkable to get from just an image of a speck of sand. So what are the future applications of something like this? What we could envision in the future is a case where we just use smartphones, we take a picture of a sample of sand, and we get instant classification. Because 85% might not seem high enough for a single speck of sand, but imagine now a voting algorithm that would essentially evaluate multiple sand particles within an image and then vote and say that, you know what, based on all of those particles there, I think this is the type of sand that we have. So imagine now more reliable characterization of soils at the point of drilling, when right there when we're drilling a borehole. Imagine having some kind of a handheld device that can classify soil right there on the spot. And then this could be extended to also have many other potential applications as well. So this is as far as AI is concerned, you know, the part A of advanced data analytics. What about part B? I think it's equally important, this automation. There are countless cases and many studies that we did and we're currently doing at this time where we had to do some high-level analysis on the behavior of piles in this case. This required batch processing, and no commercial software right now does batch processing, at least to my knowledge. And what I mean by this is some kind of application where you would fit 1,000 projects and you would get 1,000 calculations instantly in terms of the pile, the calculated capacity of that pile. So this, you might think, is perhaps something not so important, but it is really important, batch processing, because it can help in situations such as designing piles for the solar panels at solar farms. And if you're familiar with this project, this is something that has very thin, it's a project that has very thin margins when it comes to profitability. So in that case, imagine having some kind of a batch processing algorithm that can run through all of the pile capacity calculations individually for each one of those panels and reach a more optimized design that will improve constructability as well. So we use this for different studies, and this actually, I'm looking at it and it's becoming quite old now, this study on piles. And another example also on how this efficient automation part of advanced data analytics can help is this example that you see here. So this was a study on seismic earth pressure. And if you've ever run calculations that deal with seismic earth pressure, they can be quite daunting with a lot of sines, cosines, and whatnot. So it might take a while to run all of these calculations by hand. And usually we run them for a set of conditions and then we say good, no good, and move on. So in this case, this was such a simple idea. We said, what if we just build a quick interactive application where we can adjust the input values, we can adjust everything there and see how seismic earth pressure changes. And this led to some remarkable insights just by building an interactive dashboard by hand. And the calculations are, as I mentioned, extremely complex, especially for multiple layers. And in this case, the interactive tool, what it did is it helped to demonstrate the nonlinearity of the stress distribution, which exaggerated for conditions with large cohesion and steep surface slope. Also, this interactive Moore circle plot that we had there, excuse me, helped identify conditions where they were essentially inadmissible, where we would be outside of the conjugate stress line. Such a simple thing, interactivity enabled by computer programming, which helped us discover some new insights. I'll go through data management quickly in the interest of time, and also because Bob did such a great job presenting this. But I'd like to offer just my quick thoughts on this. Now, the way that you should view your data, data is a fuel that powers any analytical workflow. Without data, we don't have analytics, plain and simple. And whenever we want to design a data management system, there is a very simple rule that I like to follow, and I present this to everyone I work with. So some people come to me and they say, yeah, I have data. I have spreadsheets, I have PDF files. And I say, yes, you have data, but perhaps you have information, but not really data. The way I define data, it means that it's in a form that is queryable. So in databases, if you really want to have data in a proper format, the rule is everything must be queryable. You might have 1,000 spreadsheets. If I cannot look up values within those spreadsheets in an automated way, then that's not good. If you have PDF files, but I cannot query, I cannot write a query, a small bit of computer code that can fetch values from those PDF files, then that doesn't do much. In order to get to the point, we have to follow what is called ETL, extract, transform, and load. It's a very tedious process. It's one that takes oftentimes the majority of the project time, but it's extremely important. The benefit here is that we type once and we use many times. Now, if the previous speakers will allow me, I want to a little bit disagree with the term big data within geotechnics. We have big data. We have big data in IoT, anything that relates to sensor data and predictions based on that. But in our day-to-day, we primarily, as geoprofessionals, work with not so big data sets, but highly complex. And that is often a challenge. We're working with data that we cannot afford to disregard if they have missing values or if they have inconsistent values, because we don't have a lot. In other fields, they have this luxury, in my opinion, to just have a data set of billions of entries there of records, and they just eliminate some to get accurate models. We don't have this option within the geoprofession, at least to my experience. And when it comes to building those database management systems, there are a lot of benefits to going the relational route, but NoSQL could be just as good. So here's very quickly the process of extracting, transforming, and loading data. It's not always in that order. Sometimes it could be transform, it could be load and then transform. But in general, what ETL means, it means we have a well-structured data source, database, and what we do is we load data into this database from multiple sources that need to, where we need to apply some kind of transformations. And besides databases, I wanted to make the case of data warehouses and data lakes. And this is important because this is data warehouse is where an organization within the geoprofession wants to get to, but they might not be ready for it yet. Building a data warehouse is, it's a very tedious process. So oftentimes what we do is, instead of planning for a data warehouse and missing a lot of data capture, we launch a data lake immediately and then move on to build a data warehouse. And what this means is a data lake essentially, in very plain terms, is a file system where we load the data and then we can process the data at a later time. Bob mentioned digs, and so with that, I'm not going to say anything else because I still have a lot of slides to go through. But the only thing I'm going to say is please do not disregard digs. It has a lot of potential. I added another link here, which is the GitHub repository, and we absolutely welcome any suggestions or help when it comes to digs. All right, so we talked about opportunities, we talked about benefits and some examples. Now, if you have no idea how to get there, let me show you how you can get started. There's a bunch of learning resources out there, and online education has revolutionized many aspects of our learning options. And in this case, you can go from having no idea how to apply machine learning to actually applying some very complex machine learning models in the span of a few weeks or months, depending on how committed you can be. So what I have here is a list of learning resources, which I consider top-notch. And for most of them, you don't have to spend anything. These are free resources. It's absolutely amazing. So 2 courses from EDX, the best Python courses out there by far. And then I think pay attention here to the sequence as well. First, a little bit of programming, then probabilities, and then machine learning. You cannot go straight to machine learning without some basic understanding of probabilities. So after you've mastered all of this, there's a fantastic series of courses on deep learning AI by the legendary Professor Andrew Ng. And anything you take there is just going to benefit you. And also pay attention to this platform here, Kaggle. It's a great place to practice. Speaking of practice, I mentioned before that my goal is to make machine learning commonplace in the Geoprofession. For those of you out there that perhaps have started already with machine learning, I'm sure you, at some point, let me just set the background a little bit. So as with any learning journey, whenever you start building and practicing on a new skill, you have to find other examples in order to practice. So if we're learning soil mechanics, we have our textbooks, they have examples in there, and practice homework, we have to go through those. Now with machine learning, there's a bunch of toy data sets out there that we can use to practice. But if you are from the Geoprofession, you often realize that practicing on toy data sets that are of the kind flower shapes or hand character recognition or housing prices, this is all great. You can still learn a ton. But what if we had geotechnical data sets that we can practice with? And how there are all sorts of data sets out there in geotechnics. And the importance of toy data sets, it goes beyond practicing. It's also good for benchmarking, for running competitions. And if we look at the effect of open source data sets in other fields, they have largely acted as a catalyst in the digital transformation of those fields. So the evolution of deep learning is in many ways based on high quality open data sets that researchers around the world had access to and could play with. So there is actually a singular, I should say, good example in Geotechnics. Whenever you want to look at the advances in using programming and machine learning in the Geotechnics, it's good to look at our Dutch friends. I think they're a little bit ahead of everyone else. So in this case, Bruno Stuitz, I haven't had the pleasure of interacting with him. He created actually a competition on Kaggle. It was part of a conference that was delayed. Hopefully it's going to be held this year. And part of this competition was working with a data set that he provided in order to run predictions. So this was one example of using a GeoTech data set to practice with machine learning or other methods if this is something that you want to use. And you can see here it was highly popular. 61 teams actually participated. So a lot of challenges with collecting data sets that we can use to practice machine learning as geoprofessionals. So what was the solution? The solution for me was to launch an open source Python library that I called MLGO. And it's very much the basis of a hopefully collaborative project, which is going to serve as a tool for everyone out there that wants to get started with machine learning within the geoprofession to just have some relevant data to practice with. And the way I structured this, it just has a single data set right now on pile data. This is some data that I used to work with in the past. And I'm going to keep adding more data sets as we go ahead, and you can send me your data sets and we can add those in there as well. But the idea here is convenience. If you worked with Python and machine learning, there are some very popular libraries that help with machine learning, scikit-learn, TensorFlow, for example. All of these libraries have toy data sets built in. So I copied this functionality and I said that, you know what, if you just install MLGO, you can load data sets and go. And then you don't need to go out there, see how someone saved their data set. Was it CSV, Excel? What were the headings? What was this? What was that? You don't have to worry for any of that. And hopefully, if you're interested here in following this journey, this could be a tool that you can use. And if you want to contribute and add more data sets there, please reach out. I'd be happy to help. There are some very good libraries for Geotechnics, Python libraries, I should say. And again, Bruno Stuitz has this library called Groundwork, really good library. GemPy is another one, very important. Plaxis has a Python connector. So if you're out there running a bunch of finite element models, then you'll find that you can actually improve your workflow just by picking up on Python and building your own custom workflows that run on Plaxis. So they saw the value there and they kept going. And have my own set of libraries, and I'm doing some work on that right now that's going to go public soon. So in conclusion, let's focus now on some of the challenges in this process. So there are tremendous benefits in just enhancing our skills, picking up on a little bit of programming. You don't have to be actually an expert in software engineering. I'm not saying that you have to go out there and become software engineers. No, this is just a working knowledge. The same way that you learned other software applications in order to do your day-to-day, to accomplish your day-to-day tasks, this is just one more tool that will complement your skills. Now, on this, I've had students who were actually very enthusiastic and they became very good programmers. So that's, it's out there and everybody can choose what they want to do. Now, in order though to get to be at the forefront of the digital transformation of the geoprofession, there's no way you're going to do it without data. So within your organization, as Bob pointed out, you must focus on the data. You must build a robust data management system. And there are many solutions out there. Be careful with what you choose in terms of a solution. Your question to whoever is selling you a data management solution should always be, can I query everything I want in here? That's the only way you can do it. And can I do it easily? Now, I mentioned earlier, going from proof of concept to actually marketable and reliable predictive solutions, this is a very intense process. And it's going to take a while to produce results. So it's important to actually stick to it. There will be also cases, because every project is unique, there will be cases where significant effort is put forth to produce reliable predictions, but we might fail to do so. Every project, this ties actually directly to the whole concept of deep tech that I presented earlier: high risk, high reward, and also intense research and development. Essentially, there's always risk of failure. But the idea here is that it might fail to produce predictions, but I guarantee you that in the process of testing, you'll find that there will be a ton to learn that will help in another project. Now, this is all brand new in our field, and first in the market. Being a pioneer means that you have to pave the way. So you'll have to convince clients of the benefits, and there's a chance that after you pave the way, someone else is going to see the value and just compete without needing to pave the same way, because the clients that you try to convince, they already see the benefits. So this is the pro and the cons of actually being a pioneer. Trust in the system, very important. False positives are as dangerous as false negatives, because what we're doing here is we're trying to productize AI, build a reliable system. If the system doesn't work, sometimes that's really not good. And the challenge of actually productizing AI is that, first of all, we are in a niche business. Geotechnics, it's not a scalable business as it is in other areas. So building an AI product that's going to cover multiple cases is going to be a challenge, but there are some ways there. There are some things that we can look into. Stay focused. That's also very important. As you're building your skills, you're building your teams, you will realize that the capabilities of what you can do become greater and greater. And then there's always going to be those shiny objects that you want to focus your attention all the time, but you have to be very focused and finish the task at hand before moving on to the next one. Leadership might not see the long-term return. I actually have a typo there. I'm going to fix it. And the more important thing in the end is we have the question of who owns the model. If you build it internally, obviously you own the model. But if you outsource the process, who owns the model? If you don't have the capability of building those predictive models in-house and work with other consultants, who will own the model in that case, and who will vouch for it? So these are issues that we at Groundwork A.I. have been thinking for a while, and we think we have the solution to that. Now, some positive thoughts, and this is my last slide. There's a ton of interest in AI and machine learning. I've been focusing on this area for a few years now, and it went from me being the only person presenting to a conference to now steadily having a lot of presentations that have proof of concepts at conferences. And as I mentioned, it's absolutely okay to set ambitious goals, because there's a ton to learn in the process. You'll hear a lot of people who say, why do we want to go to the moon? Why spend all of this money to just go to the moon? The point that's lost there in some cases is that in the process of building the technology that's going to get us there, there are so many other innovations that are going to pop out and help humanity in many different ways. So same way, you can set ambitious goals within your organization, and in the process of achieving those goals, you will enhance your methods. You will set up the groundwork essentially in achieving so many other things. Now, choose the right tools for the job, very important. It's not always machine learning. Maybe there are other ways to do things. And on a positive note, because a lot of the people I talk to, they're lost. They don't know how to get started. My answer there and my encouragement has to do with the fact that engineers in general, in my opinion, apply some sort of algorithmic logic every single day. Whether that is, what is a design manual? A design manual is a cookbook. It has recipes on do this, if this, do that, if that. If we just translate a design manual into computer code, that's basically it. We have an algorithm. So engineers apply algorithmic logic every day, and I see from my students that when it comes to picking up a little bit of computer programming, they have absolutely no problem. And finally, again, in my opinion, the only missing piece to achieve this true human-machine synergy is ambition. It's not a technology or a technological hurdle. It's just ambition. So with that, thank you very much. And if you have any questions, I'm happy to take them. So the geoprofession, geotechnical engineers in general, it's always a constant struggle against the unknowns that we face with subsurface conditions. So by having predictive models that learn essentially from past performance in similar conditions will absolutely help in many ways in reducing those uncertainties and increase our confidence essentially in the predictions that we get out of this. So I'd say the benefits are cover a lot of cases. I mean, think of all of the methods that we use. Many of the methods that we use actually are empirical or semi-empirical methods. So what are these methods? These are methods built by legends who had a very intense and intuitive understanding of fundamental principles and how the soil behaves. And they produce those methods for others to use, where essentially they translated their experience and their lab tests and pile tests into graphical methods or other design methods that we can use. So the fact that these are empirical or semi-empirical methodologies, they actually lend themselves to be renewed, let's say, with data and machine learning, because machine learning is learning from experience in many ways. So in terms of software, I don't use anything commercial. So anything that has to do with analytics, I build it using open source libraries. So whether that is TensorFlow, Scikit, which actually are the most popular ones. I don't use any other software. So the accuracy that we got from that was in the order of 85%. And that's though from a single speck of sand, just a 2D projection, an image of a single particle. So it's not on the level of 95+% accuracy. Maybe we could get there actually. With the process of evaluating convolutional neural nets is a tedious one afterwards, because what you have to do is you have to go in and see why there were some misclassifications and see what it is that the model did wrong or did right. So there's a lot of improvement there. But I think 85% as a first attempt is encouraging in the sense that in real life, you're not going to classify soil based on a single particle. You look at multiple particles within an image or within a matrix, essentially. So in that case, combining the confidence from multiple analyzed and classified particles is, I think, what is going to give a much higher accuracy in the model. Yeah, so I see, again, it was a point I made about the fact that I really wish we had big data within the geoprofession, but that has not been my experience. So yes, we have sparse data. and we cannot lose anything. We cannot miss anything there. So one of the first mistakes I see in papers that I review in journals and at conferences as well is I see some very ambitious teams aiming to use some very complex neural networks on data sets that have 100 data points or less. And this is something, it's a scarce data set, and you're thinking, well, you probably use the wrong model there. This is not enough. There's not enough variability or data in there to tune all of the parameters in the model. At the same time, though, there are other models that perhaps could work with scarce data sets. So if we look at decision trees and other models, these tend to perform well in certain conditions with scarce data sets. So there are options out there. There are things that we can do.
So what I was thinking about only what Nick said about using open source software, that's very important. And another thing, collecting the data, as I said, is a big challenge. Sometimes many of the client does not want to share the data. So that's a very big challenge, and so there should be some initiative in transparency in data. That's, I think Nick will agree with me, that's a big challenge.
In the US, it's a massive challenge. In Europe, not so much, but in the US, it's a very big challenge. Everyone tends to hang on to their data and they don't want to share. I had multiple cases where I was working with contractors and other companies, and they just didn't want to share for their reasons. But in Europe, it's different. So I've given this presentation or parts of this presentation where I had more of a European audience, and they actually took offense to that point, where they said that, why are you saying that there's no data? Look at these data sets that we have. So in Europe, it's a much more different situation.
At least you could say that somewhere the data is available. Because I have struggled a lot 20 years before. Actually, I was writing to many people, I need this data, that data was not there. I was trying to scribble through the books, journals, to collect the data. So over the years, many things has come online, that is helping. And actually, your talk was really interesting in terms of making it like convincing the professional engineer to use it. That's very important. If they can really start using, then there will be a big initiative in, AI and big data in geotechnical engineering. Because as you said, we are using empirical, semi-empirical methods, but still we are not accepting this AI, particularly the professional engineers. But it is better to show them that, in fact, when instead of using empirical or semi-empirical method, the AI technique has much better efficiency in that respect. That's a big challenge, and your initiative will really help. And it was really convincing. Your talk was really, convincing to the people, like those who are attending here, and that I think you might be doing also to your other clients, so that if you can, your initiative will help other professional engineers or particularly companies start using these AI techniques.
Yep, hopefully. I see a lot of good things in the future. And what's encouraging, and I'm sure you have the same experience, is I have a very positive reaction from my students. So I see a lot of interest from younger people to be more versed into using these new tools and using these new methods. And I think this next generation of leaders within the geoprofession will have bold ideas and a whole new mentality in terms of organizing and using their data. Absolutely.